Alright, welcome everyone. Today we're happy to have our own Pratik Rath, who's going to tell us about a new proposal for holographic Renyi.
Thank you for the invitation. This is going to be some work to appear with Shidong and Jonah Kudler-Flam. So let me just start with very broad motivation, the standard slide that we all use. So ADS-CFT has been super useful in our understanding of quantum gravity. It tells us that quantum gravity in D plus one dimensional ADS is equal to conformal field theory in D dimensions, which lives on the boundary of ADS. And a particularly useful approach to understanding this duality has been using quantum information ideas. So it's given us a sort of fine-grained perspective on this duality. For example, starting with the work of Ryutake Nagi and the whole HEP-QIS community, we understood that the entropy of the boundary region, say capital R, which is this region, is computed by this quantum extremal surface formula. And in particular, it also taught us that there's some sort of duality wherein the region little r, which is shaded here, is completely captured. The information in little r is completely captured by the boundary region capital R. So so viewing things from this quantum information lens has helped us in understanding the duality better. And so what I'd like to do in this talk is use more such quantum information ideas to try to understand their holographic duals and see if that helps us understand the duality better. So the quantity that I'll be talking about here is the Renyi entropy. So just to review, the Renyi entropy is a one-parameter generalization of the entanglement entropy with this index n. So distributed by this 1 over 1 minus n log trace rho to the n. So it's basically some function of the moments of the density matrix. And in the limit n goes to 1, you recover the entanglement entropy. So it's well understood how to compute this using a path integral. So in particular, computing trace rho to the n can be computed by an n-sheeted partition function. So it's a partition function on an n-sheeted manifold which has branch cuts at R. So what you do is take n copies, glue them across the region that you care about, capital R, and the path integral on this manifold computes trace rho to the n. Then you can just take the log and compute the Renyi entropy. And this can be done at integer n, but then you can try to extend that to non-integer values of n by some continuation. In the context of ADS-CFT, this partition function, the boundary partition function, gives us boundary conditions that can then be filled in by bulk geometries. By the ADS-CFT dictionary, the partition function Zn is related to e to the minus I of Gn, where Gn is the saddle point or the solution to the gravitational equations of motion with the appropriate boundary conditions that have been set by the CFT path integral. So we know how to compute Zn, we know how to compute Gn as well at integer n. It's a well-defined problem. But then in the bulk, we also know how to do better than that. So in 2013, Lukowitz and Martesena proposed a natural way to continue away from integer n. And the proposal was as follows. So the path integral that we're doing on the boundary has a Zn replica symmetry. So for example here, if you just think about the boundary path integral, it has some sources, but the sources are inserted in some Zn symmetric way. So here n equals 4 and we have 4 of these copies which are glued together in some cyclic fashion. Since the boundary conditions are Zn symmetric, so the insight was to assume that the bulk solution preserves this Zn replica symmetry. And once you preserve the Zn replica symmetry, you could equivalently just think about taking a quotient and looking at one piece of these. So this, the action of the action of the total solution is just n times the action of one of these pieces, which has an opening angle of 2 pi over n, n being 4 here. But this problem now, phrased in this way, is easy to analytically continue in n, because all it said was we have the boundary conditions that were obtained from preparing one copy of the state, but apart from that, we impose that there's a conical defect with a specified opening angle 2 pi over n. But that's something that integer n is not special to that, and you can analytically continue this n away from integer n, and so it gives you a bulk proposal for computing the Renyi entropy at arbitrary values of n. That was the Lupitz-Martesana proposal. And in particular, you can also, what Dong realized was there's a slightly different quantity, which is called the refined Renyi entropy, where you take some derivatives with respect to n, but the advantage of constructing this quantity is that the only contribution that you pick up in the bulk is from the area of this cosmic brane. So it's something which is similar to the Ryuta-Yanagi formula, and in particular it's like a one parameter generalization of the Ryuta-Yanagi formula itself. So the formula just says that the refined Renyi entropy is given by the area of this cosmic brane divided by 4G. So this was all stuff that was done 10 years back.
And
yes.
Yes. So the area will still depend on n, right?
Yeah.
But this refined Renyi entropy is not the same thing as the original one. So it's just another thing that also approaches the correct answer as n goes to 1.
So the area depends on n. So clearly, like once we change the number of copies, or we just tune the opening angle, there's back reaction from that brane, and so the full geometry changes in response to that. The Renyi entropy was computing the action of this solution, which includes both the bulk part of the action as well as some contribution from the defect. And the advantage of constructing this quantity was you basically drop out that bulk term. So all it depends on is the value.
But this quantity, I guess what I'm missing is this quantity must have some good properties that, I mean, you can consider any quantity you want to. You could have just not included the bulk term. But why is this a good quantity to consider in addition to being more? It's only interesting. It's not enough for it to be simpler, right? It has to do something. Presumably n goes to 1 gives you the...
Yeah, so certainly, yeah. And as n goes to 1, this also gives you the 1 number entropy. So it's another different generalization that you could write down.
Okay, so that would carry on. I mean, it's just as good as the Renyi entropy in terms of limiting to the phenomenon entropy,
yes.
But it's simpler to compute in the bulk.
Yes. Yeah. That's right. Okay. So good. So this was all 10 years back. So why am I giving this talk? Well, so there's some issues with this proposal, and to highlight that, let me talk about a situation where we have multiple extremal surfaces. So let's say we have the classic situation of two intervals in the vacuum. So R is these two intervals, and then there's two candidate RT surfaces. There's this gamma 1, which is the disconnected one, and gamma 2, which is the connected surface. The Ryuta-Yanagi formula tells you to compute the minimal area surface. So depending on which area is lesser, you pick there can be a phase transition between these RT surfaces. And a similar story holds for the Renyi entropies as well. So there's some sort of transition between the connected and disconnected phases. Now, if you look at the action of the saddle that I showed you in the previous slide, near n equals 1, the action of this is given by n minus 1 times the area over 4G. And this just comes from computing the action from near the defect. And for n greater than 1, minimizing the action, so since this coefficient is positive, minimizing the action is just equivalent to minimizing the area. Since you have two solutions, one with the cosmic brane on the disconnected surface and one with the cosmic brain sitting at the connected surface. You can pick these two candidate saddles, minimize the action, and you get the minimum area criterion just comes out of that. But if instead I was continuing to n less than 1, naively, since this coefficient is negative, it would require a maximization over areas. And that is a funny rule, and it's demonstrably wrong in certain cases. So for example, in fixed area states, you can show that this is the wrong rule, and the correct rule in those cases is to still continue picking the minimal area surface. So there's something funny happening as you cross n equals 1. But that doesn't kill this proposal. You could just say, for n more than 1, let me minimize the action, but for n less than 1, let me instead maximize the action. That would land you on the minimal area surface either way. So it's sort of continuous across n equals 1. So it doesn't obviously fail based on this example.
Yeah, I missed something. You said earlier it does obviously fail. You must have switched to the statements in which so it says here this is demonstrably wrong in certain fixed area states.
Yeah.
What is the thing that is demonstrably wrong?
So the thing that's demonstrably wrong is, so in a fixed area state, you can compute the full spectrum by using different methods. When you compute that, you know what the answer for the Renyi entropy is at arbitrary n. And you can check that for n less than 1, the answer is still the minimal area over 4G.
Yeah.
But this rule, if you were just naively minimizing the action, this would give you the maximal area over 4G. The usual thing people do is just minimize the action. So that would give you the wrong answer. So that's obviously wrong.
And you're proposing switching the rule when you cross n equals 1 from minimizing to maximizing.
Yes. So that would at least save you from this issue. If you switch the rule, so if I say that for n less than 1, let me maximize the action, then at least it's consistent with this fixed area answer.
But that's what you don't want to do. You do something else. Or
Yeah, this is not going to be the final answer. Even this is not going to be sufficient, but let me give Lucas and Madison the best chance to succeed.
The bottom n greater than 1 should be n less than 1.
Sorry.
There's a typo where
The last.
should be
Oh,
maximized.
sorry. Yeah, this is n less than 1. Thanks.
So just to understand the philosophy, is the idea that you want a prescription that works for any value of n, larger or smaller?
Yes.
Because I guess like n larger than 1 has a physical interpretation, and smaller than 1, at least I don't know if it has a physical interpretation. N equals 2 is something related to the purity, but n equals half, 1/2, does it have any physical interpretation?
For example, n equals 0 would be like the rank of the density matrix or something. I mean, if you want, then we can think about the case where it's a thermal density matrix or something, and n is just tuning the temperature. So there's nothing special about n more than 1 versus n less than 1. Both of them just measure the entropy at different temperatures.
Right. Okay. So you just want something that works for anyone.
Yeah, so the question is like, if I just want to compute the holographic Renyi entropy, how do I compute it? So with this rule, it doesn't obviously fail, but then there's other examples where it fails. And the example, so one of the examples is of the PSSY model. In the PSSY model, we have JT gravity coupled to end of the world brains, and the end of the world brains have some number of flavors. These flavors are entangled with some reference system capital R, and again in this situation, this is the phase curve calculation where there's two different quantum extremal surfaces. One is the empty set, and one is the horizon of the black hole. And these gamma 1 and gamma 2 basically play the same role as the gamma 1 and gamma 2 in the previous situation. The only difference here is that in this case there are actually thermal fluctuations. So the system R bar has a thermal spectrum as opposed to a fixed area state where you're sort of working in the microcanonical ensemble. But still, it's still a situation where you can compute all the moments of the density matrix and just compute an arbitrary Renyi entropy from that. That can be done by independent methods like the resolvent technique. Now, when you do that, what you find is for any n less than 1, the naive answer, that's the Lukowitz-Madisena answer, would say you have you take the minimum of log k, which is the entropy associated to gamma 1, versus the thermal entropy coming from the black hole horizon. So that gives you this curve. But when you actually compute it, there's this whole region in the middle, which is a sufficiently big region. So it's a region where there are, which is sufficiently far from an entanglement phase transition. It's not right at the page transition or something. It's like a wide window around the page transition, where there are corrections of order 1 over g. So it's a leading order effect.
You're taking temperature of the JT gravity model to be high, it's order 1 over g.
The temperature, I'm taking the temperature to be small.
Where you said it's order 1 over g, so there's a few ways you can get things you can think of as order 1 over g. JT could be S naught, I don't think it's...
Yeah, so S naught is what I get.
Yeah, sorry, you're claiming the corrections at order S naught here. Is that correct?
Sorry, they're order 1 over beta.
The order 1 over
Order 1 over beta,
yeah.
yeah.
And you're thinking of features order 1 over g is, sorry. But then I think, sorry, if they're order 1 over, yeah, okay. Go.
So it's a leading order effect. So there's some similar effect that you find for the entanglement entropy itself, but that's of order 1 over square root g. This is instead of leading order, and it's over a wide window. So there's a large region where this cosmic brane proposal fails. Even this updated version where we maximize for n less than 1 and so on. And you can see the same thing in the refined Renyi entropy, where the naive curve is different from the actual calculation.
What's the value of n that you're plotting?
Yeah, this is for generic n less than 1. Any n less than 1, you see something like this. Doesn't matter.
So n less than 1 is important?
N less than 1 is important. What happens is, so basically, what happens is...
Does the badness turn on continuously as you cross 1, or is it like, is this some order 1 distance from n equals 1?
Yeah, so the badness turns on continuously as n. So what happens is, so there's these two phases, 1 and 2, where the Lukowitz-Madisena proposal is correct, and then this middle phase which I've called D. And what happens is, as at n equals 1, they sort of agree, so they're sort of at the same point. And as n is lowered below 1, this D region sort of gradually opens up. So
This is coming from the Renyi entropy get dominated by two different sets of eigenvalues, is it?
It's not two different eigenvalues. I will talk about what it's dominated by.
So there's always a disagreement, but it grows in a less than 1,
Yeah.
but in other cases it sort of gets closer.
Yeah, so what happens is for n more than 1, they sort of cross over the other way, so this region just never shows up.
But the exact answer is never.
Yeah, it's never king, but I'm working only at leading order, so yes, this is only the leading order. I mean, it's always smoothed out a little bit.
So this is 1 over square root of g in n greater than 1? The deviation?
For n greater than 1, there's no, not even an order, it's like an order 1 correction.
Order 1 correction.
For n equals 1, there's an order 1 over square root g correction. For n less than 1, there's an order 1 over g correction.
So this naive one is the corrected one.
The naive one is the corrected Lukowitz-Madisena.
Naive one is what you said, the refined one in a previous
that's right.
lecture.
That's right. Yes,
The refined one.
other naive one is like, just not even,
So we call refined in the previous page. Or this naive one.
Yes. So this good.
Yes,
I should probably call it like the correct answer.
That's
That's like the
one.
Lukowitz-Madisena answer. Yes.
And in the limit n that goes to 1, even from below, that gives you the right answer. From what you said.
Yeah. It'll give you the page load. It's continuous. Okay. Fine. So then what we want to do is understand these situations as well. So it's clear that the Lupin-Smartly proposal is not sufficient to get us the answer in these situations. So is there some other universal proposal which can give us this answer? And that's what I'm trying to do. Okay. So now let me just give you a broad overview of how we go about doing this. So we use fixed area states as a tool to solve this problem. The proposal itself will not be just for fixed areas, it will be for general states, but we use fixed area states as sort of an intermediate step. So I'll review the replica trick for fixed area states, and that will lead us to this new proposal for holographic Renyi entropy. And finally I'll compare this with the cosmic brain proposal and discuss when it works and when the cosmic brain proposal works and when it doesn't. Good, so let's start with fixed area states. So this is some review of work that was done in these papers. Generally, when we use the gravitational path integral, we prepare smooth states in the sense that we specify some boundary conditions at the asymptotic boundary and then integrate over all metrics and look for solution. And the saddle point is some solution to Einstein's equations consistent with those boundary conditions. For a fixed area state, in addition to the boundary conditions at infinity, we also impose some boundary conditions in the bulk itself, and those are, we fix the values of the areas of these surfaces gamma 1 and gamma 2 to some specified values a1 and a2. So in particular, so there's some boundary conditions at infinity, and then there's these two surfaces, gamma 1 and gamma 2, which have some definite values, definite areas a1 and a2, specified as a boundary condition. But you can't, that seems like an extra boundary condition, and so the cost is you need conical defects to source those fixed areas. One way to see it is I can do that by adding in Lagrange multipliers, so these mu1 and mu2, which are just setting, so in the exponent it's I mu times a of gamma 1 minus a1. The integral over mu set makes that a delta function. So what I'm doing is setting the values of a of gamma 1 and a of gamma 2 to the specified values. But equivalently, you can think about it as a source in the action, which is basically the action of a cosmic brain. And so in the saddle point solution, what ends up happening is we solve Einstein's equations everywhere, and we have these source terms at gamma 1 and gamma 2, which which give you some conical defect that allows you to set the areas to a1 and a2. Does that make sense?
And we know where those defects should be.
Yeah, so you want to specify it like gauge invariantly. So let's say we were doing this example of the two intervals, then there's some connected surface and some disconnected surface. So so on this Cauchy slice, you just look for the minimum connected surface, which is gamma 1, and then the disconnected surface, which is gamma 2. And yeah, you're fixing those areas. Equivalently, what you could do otherwise is not specify which surface, but then just think of this as a cosmic brain with some action. The equations of motion of the brain itself will set it to be extremal, so it will land on those surfaces. So there are, at least at classical level. Okay. So fixed area states gives us a useful basis for decomposing general states. So let's say I have some general state psi. It can be, so this is the basis of fixed area states A1, A2 can be used to decompose psi in this form. And these are just some phases which will not be important, but the amplitude here can be interpreted as a probability distribution over the areas. So the probability distribution can be computed by just looking at the norms of A1, A2 psi divided by psi psi. And this can be computed using the gravitational path integral. So each of these terms, so let's think about the first term. The first term, we take the overlap between psi and A1, A2. Psi has just some specified boundary conditions at the asymptotic boundary. A1, A2 has the same boundary conditions at asymptotic infinity, but in addition we specify the areas. So that just gives us the action of the saddle that I drew on this previous slide. So this is the leading contribution to the numerator. In the denominator, we just have the usual smooth path integral where we don't have any conical defects. And so that gives you the term without any conical defects. And so the probability distribution is just given by the difference of actions between the smooth saddle and the fixed area saddle.
Would that be a factor of 2 then? If we have each side would give a full Euclidean path integral. You have 2 bras and 2 cats on the bottom and 2 bras and 2 cats on the top. Maybe a bit stupid.
I think you're right. I think you're right. There's a 2 there. Yeah, there's a 2 in front of these. Thanks. Yeah. But note that the saddle GA1, A2 is a constrained saddle. It's a saddle where we've specified the values of the areas, whereas G psi is an unconstrained saddle, which is because we're integrating over all possible areas. And so this is this probability distribution. This probability is always less than 1 as it should be. Okay. So with this, so taking the state, we can compute the density matrix, and just by computing the trace over the complement region, we have something like this, and we can decompose it into 2 different terms. The diagonal terms, which just comes from setting A1 equals A1 prime and A2 equals A2 prime, plus some off-diagonal terms. That's just the general decomposition of this density matrix. Okay, so now in order to use this, so at this point we have some representation of the general density matrix associated to some smooth state in terms of fixed area states. So in order to do a replica trick for this smooth state, I first need to review the replica trick for fixed area states. So let's do that.
Okay, so,
Yes.
So the sum here is like an offer simplification, right? Should be like a
Yeah, but yeah, that's right.
Measure.
So yeah, that's true that it should be an integral, but then, so what we really want to do is think about fixed area states as not delta functions in the area, but you want some small width around it so that it still has some semi-classical description. And then you can discretize it and then sum over. That's what I'm doing. That won't.
Okay, so that's not a big.
That it won't play an important role. Yeah, it will be a subleading effect.
So can I ask?
Yeah.
It's extremely. So what's the pavitel of the overlapping of A1, A2, and psi?
Yeah, it's so for psi, let's say we had some boundary conditions with some sources or something. So this was psi, and then A1, A2 has the same boundary conditions, but in addition you want to specify the areas, and so there will be some conical defects which are specified by that. So this overlap A1, A2 psi, the saddle is going to be the same as the one which computed the norm of A1, A2 itself.
So you're writing Euclidean,
Yeah.
and then this is the boundary.
Yeah.
For A1, A2 depends on the sum. So A1, A2 depends on the sum. A1, A2 depends on the sum. A2 depends on the sum. A1, 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 A2 depends on the sum. A1 How do you know?
No, A1, A2 is something I can specify.
Why is there a boundary insertion for the bra?
Oh, that's because, so let's think of A1, A2 as a projector onto some A1, given A1, A2 acting on psi. Because we're choosing the same state, so the asymptotic boundary conditions are being head fixed, so that's psi. And you can think of the projector onto A1, A2 as these sources, which are giving you these definite values of the area. So all I'm saying is that this overlap is the same as this overlap.
Pratik, I think actually the very right hand side was a correct formula. It's the middle. The denominator shouldn't be psi squared because you've only got two psi's in the top. It should be psi A1, A2, A1, A2.
You're right. Does that make sense?
So the basis depend on the sum. Is that right? The fixed area basis depend on the sum.
Yeah. So when we say a fixed area basis, yeah, we really mean we have a psi in mind, and then we're acting with projectors on top of that. Because, yeah, like fixed area for the thermal field double would be different from fixed area for the vacuum. Alright. So good. So now we have this form of the density matrix, and we'd like to use this to compute the Renyi entropy. So, the replica trick for a fixed area state is actually really easy, and that's part of the advantage of using fixed area states. When you have, so normally when we compute the Renyi entropy, when you glue together multiple copies, there's some back reaction that you have to account for, which changes the solution in the bulk. In the case of fixed area states, it's actually simpler. All we do, so suppose we wanted to compute the Renyi entropy, all we do is take many copies of the original saddle that had a conical defect and just glue them together. Now, this automatically satisfies the right boundary conditions at infinity, and it satisfies the fixed area condition in the bulk. And so this is a valid saddle for computing trace rho to the n. So that's pretty easy, and so if you're handed the the original solution at n equals 1, then you can construct the solution for any integer n just by gluing together pieces of them. When you use that, you can compute trace rho to the n, and what you end up with is e to the minus n minus 1 times a over 4g, which is equivalent to saying that the Renyi entropy and the refined Renyi entropy both are equal to a over 4g. This is the fact that a fixed area state has a flat Renyi spectrum. It doesn't have any dependence on n, unlike a smooth state where you typically have a dependence on n just because of this effect of back reaction that changes the area of the surface. This is related also to the fact that fixed area states model random tensor networks which have this feature of flat Renyi spectrum. Okay. So this was for the case of a single extremal surface. Let me just say what happens for multiple extremal surfaces. You can draw similar pictures, but now you have more conical defects, and because you have more regions in the bulk, you can glue them in different ways. In the single extremal surface case, the cyclic gluing is pretty much the only thing you can do. In the case of multiple extremal surfaces, you can glue them by a choice of permutations, and this is basically, these are, the dominant permutations here are basically what are called the non-crossing permutations. In this talk, we're going to work far from the phase transition, and so any of these replica symmetry breaking permutations is going to be subdominant, so I'll ignore those. And all I really care about is the replica symmetric saddle. So there's only two replica symmetric saddles, one where you glue things across gamma 1, and one where you glue things across gamma 2. There's just two of these replica symmetric saddles. So when you use that, compute the entropy similar to what I just said, you find that the Renyi entropy is given by the minimum of the areas A1 and A2 over 4G at integer n. At integer n, you can compute it using the path integral. And then you need some continuation, but there's arguments from the random tensor network that you can basically just solve for the full spectrum. once you obtain the spectrum, you can check that this is true at arbitrary n. So even for n less than 1, where there was this naive issue of maximization, the correct rule is to just minimize over the areas. So this is something we can be reasonably sure about. So for the fixed area state, this is the correct dual of the holographic Renyi entropy. And now let's try to use this to get a proposal for general states. So in order to do that, I'm going to first reformulate the original cosmic brane proposal in this fixed area language, just to contrast with a different proposal that I'll make. So in terms of the fixed area decomposition, the Renyi entropies can be thought of as maximizing over different choices of the area of this functional. So this functional is essentially a rewriting of the action. You can think about the probability distribution shows up, that's roughly computing the bulk action, and there's some piece which is coming from the conical defect. So in this maximization, what you're doing is first maximizing over different values of A1 and A2. Let's just look at that at n equals 1 first. So n equals 1, you drop this term, and you're just maximizing over the probability over A1 and A2. What that does is just give you the smooth saddle. So that's just the Gibbons-Hawking prescription to get the leading saddle. When you now change n, then there's this sort of force term which changes the area, and what it does is you can think about it as shifting the conjugate variable. So the conjugate variable of the area in Euclidean signature is the conical defect. So a shift in A, so this term which is linear in A will shift the conjugate variable, which is the conical defect, by a fixed amount. When all of that is put together, this first maximization just lands you on the saddles that were proposed in the cosmic brane proposal. So in particular, there'll be two saddles for each surface. For each surface, you have the saddle where there's a conical defect with opening angle 2 pi over n, whereas the other one is just smooth, and vice versa. So there's two such saddles, and then the rule was we maximize over the choice of surface. So we first look for the leading saddles and then maximize over the surface. Does that make sense?
That is the entropy for a fixed area.
No, I'm just reformulating the entropy of a smooth state as Lucas Madison will tell you, but in the language of fixed area states. So any smooth state will have some probability distribution over fixed area states. So that's this probability distribution. And what I'm saying is maximizing over the areas of this function just lands you on the cosmic brane saddles, which have a cosmic brane of particular tension. And then finally, this maximization over the surface is the second step, where it's just minimizing the action, computing the minimal area surface.
So we maximize over A1 and A2, we are, they can be at different positions. We know where gamma 1, gamma 2 are.
So we're fixing the locations of these surfaces in the sense that, let's say we're looking at the disconnected RT surface and the connected RT surface. But when we change the areas, the whole background is changing, right? So the whole geometry is changing because of back reaction. And so the saddles would look like this, right? So there would be some conical defect at gamma 1 and some conical defect at gamma 2 for any given value of A1 and A2. But when we maximize over A1 and A2, suppose there was this term wasn't there, so let's say we're at n equals 1. Then when we maximize over A1 and A2, what we land on is just a smooth saddle where the conical defect just vanishes. But now in addition, when we're computing the Renyi entropy, we have this sort of force term, which, so for example, if I said I equals 1, then there's a potential for A1, which will give you a conical defect at A1, but then you'll have a smooth saddle at, it'll be smooth at A2, and vice versa. So there's two saddles, one which looks like that, where this is gamma 1 and gamma 2 is smooth, and the other one which is where gamma 2 has the thing and gamma 1 is smooth. And those are precisely the two saddles that Lupitz and Marasena would consider. So this first inner step is just giving you those saddles, and then the outer step is just the maximization or minimization over the action.
With cosmic brand proposal, you're saying minimizing the thing, or maximizing.
Yeah, so again, so I'm using that slightly outdated version where for n more than 1 we minimize the action, and for n less than 1 we maximize the action. So that's where it is. That's right. Okay. So importantly, yeah, the process was we first maximize over the areas and then maximize over the surface. That's the important part. So now let's see what our proposal is. So our proposal was to take trace rho to the n. So we want to compute trace rho to the n, but we have this expression in terms of the fixed area states. So we have these diagonal terms and some off-diagonal terms. When you compute trace rho to the n, the off-diagonal terms always gives rise to replica symmetry breaking terms. And so we're going to ignore those. That's sort of part of our proposal. But we'll keep all the other terms. So what we do is keep all the replica symmetric terms, which just come from the diagonal terms. So we have a maximization over all areas of p to the n times trace rho to the n. Now this is just, we can just directly take this and compute the Renyi entropy. And use the fact that we know what precisely the answer is for the fixed area state. So for the fixed area state, we know that the correct answer is the minimal area. Yeah.
Is there a reason to expect that these replica symmetry breaking terms are subleading, or is there other reasons?
So the philosophy is like we want a minimal update on Lupitz Marasena, which reproduces results where it doesn't work. In principle, you should be including these replica symmetry breaking effects. They're harder to implement, and also then the analytic continuation becomes harder. But this will work for our purposes in the sense that for example, for the PSSY, it will give you the correct answer, even without including any replica symmetry breaking terms.
So you can use that as a signal that represents.
Yeah, it's sort of so we sort of assume this and then show evidence for it, which is that it reproduces all known results. But in principle, you should include. The gravitational path integral should include everything. But this is like the simplest thing you can do, which works. Okay, so for trace rho to the n for a fixed area state, we know that the minimal area surface is the thing that contributes. So just taking this, what we get for the Renyi entropy is we maximize over the areas of times this function, which includes this minimization over areas. And the reason there was this minimization over areas was because it directly came from the minimization over areas for the Renyi entropy of the fixed area state. So the order in which we're computing the Renyi entropy is slightly different. So here we're first minimizing over the areas, computing this function, and then maximizing over the areas. This is different, of course, from first maximizing over, so here it was sort of an unconstrained maximization, where we first maximize and finally then minimize over the surface or maximize over the surface. And so, and then there's a similar formula you can write down for the refined Renyi entropy from this. So let me, at this point it might seem a little abstract, so let me talk more concretely about the comparison between these two proposals. So both of these proposals are some optimization over this function which you should roughly think as the action of these samples. What we did in the cosmic brain proposal was to just optimize this over all areas in an unconstrained way. So Yeah.
Your proposal is not optimizing this function. Right?
It is.
But it's a minimum of
Yeah.
right.
That's right. So,
That's
so what I'm saying is, you can understand that as doing a constrained optimization of this function, where you just restrict to the region. So let's say you just have an A1 here, you just restrict to the region where A1 is less than A2.
Then it's
So yeah, so I mean, just to compare them.
So, Pratik, I think I lost you.
Yeah.
In the case where you're dealing with fixed area states, the
Yeah.
probability distribution is just a delta function.
Yes, that's right.
And in that case, do any of these subtleties that you're solving here arise?
No.
No. Okay, that I see. So that's why I really need to worry about this. Probability distribution.
Yes.
There's no, I see, there's no way to, you can just get your usual flat spectrum and everything always is correct.
Yes. Good. So in the cosmic brain proposal, we have an unconstrained optimization of this function. So we integrate over all areas. That gives us these cosmic brain proposal candidates where we have a conical defect at either surface. But it's unconstrained. There's no constraint on what the areas have to be. Whereas in this modified cosmic brain proposal, we're restricted to the region where this AI is the minimal surface. So if I want to have an A1 there, then I need this region where A1 is less than A2, and vice versa. So it's obviously, I mean, clearly it's not always going to be the case that the constrained optimized problem gives you the same answer as the unconstrained optimized problem. And what you can prove is that if either, so there's two cosmic brain proposal saddles, right? So there's one where the conical defect is at gamma 1 and the other one where the conical defect is at gamma 2. If either of them satisfy the criteria, so if this one satisfies A1 less than A2, or if this one satisfies A2 less than A1, which is to say that the conical defect lies at the minimal area surface, then these two proposals agree. So nothing goes wrong as long as the location of the defect is actually the minimal area surface in that geometry.
I'm a bit lost over, at some point you've got to be scanning over these areas, over each one of these areas, right?
Yes.
Distribution.
So the optimization problem is scanning over all those areas and looking for the best solution.
So the truth is that you have only one function in F, where the last time is already minimized, but the previous thing doubled to F1 and F2. And in the end, you showed something. That was about thing. I mean, you had only one F in a sense that, right, throughout the process, the last time is already minimized, and it's only one function.
That's right.
That's the right procedure.
That's right.
But somehow you don't want to use this A1 and F, then F1 and F2 and both, and then finally choose maximum.
Yeah, that's right.
And that was about it.
Okay,
Yeah.
so we also already understood this, but can I phrase my confusion like this? If you're going to scan over A1 and A2,
Yeah.
and that's part of one of these proposals at least, probably.
Both of them scan over.
Then I don't understand how you can say that if A1 is less than A2, the proposals agree. Because for both of those proposals, there will be regions that you're scanning.
Oh, so when I say, the saddle has to satisfy this constraint. So the saddle is, when I scan, so for the cosmic brain proposal, so I have there's some A1, A2, and the probability distribution is smeared over the whole region. So I look for the optimum of this, the unconstrained optimum of this function, and let's say for this being A1, I locate it here, which satisfies A1 less than A2. Then this would also end up being the correct saddle for the constrained optimization. And so these proposals agree.
One way to think about it, I think, is if you have the smaller area surface, you're inserting cosmic brain.
Yeah.
At a certain point, that cosmic brain is going to cause that surface to become bigger than the other one. When you reach that point, you need to start adding a cosmic brain to the other one.
Exactly. That's exactly. That's exactly.
When you reach that point, you
need to start adding the cosmic brain to the other one too, so that there's not a transition in the RT surface. So introducing this cosmic brain,
that's exactly.
Want to make a transition happen at a certain point, you've got to add another cosmic brain to stop, to restrict states where that transition hasn't happened.
So for the most purpose, like, so when we talk about n more than 1, the effect of adding a positive tension cosmic ring is typically to reduce the area. So this is never a problem. So as we keep increasing n above 1, the location where you add the defect is only getting lesser and lesser in area, so it satisfies the constraint. Whereas if you go for n less than 1, then the effect of adding a negative tension ring is to increase the area. So at some point, suppose you started from the minimal area surface, the tension keeps increasing the area, and so they'll hit a transition. So, but you still want to keep this as the RT surface, and that's precisely what's happening. Yeah.
So to make sure I understand that, are all of the like correcting terms that we're ignoring ones where we sort of smear the defect over both gamma 1 and gamma 2?
That's right.
Gotcha.
So yeah, I'll give an example where we'll see exactly that.
Yeah, one question about logic. I mean, am I right? And just to make sure, like you are looking at the fixed area state and rewriting the defined or modified rubrics in some way, and you found the way to rewrite that by minimizing force inside some function. Okay, and at that point, because it's a fixed area state, it's the right thing, or both are right thing. Because it's a fixed area state. But now you take this new expression and then apply to, for example, not the fixed area state, then the two is the different answer. And you have to check that this is the right one, which you did it, but you didn't. So that's the right one. The fixed area, sorry, Ricon Marasena, true Ricon Marasena is wrong, right? All other cases. But you didn't talk yet that you'll think, because it's the same in fixed area, so you motivate it and then you check.
So I'm going to give an example where for example,
yes, without that, it's this fixed area,
it's just a proposal. That's right. Good. Okay. So whenever whenever one of the, at least one of the candidates that Lukowitz and Madison are considered satisfies this constraint, then these two proposals agree. So that's pretty much, that's a lot of examples in the literature. But this cannot be guaranteed. Even for n more than 1, we can actually construct probability distributions which violate this condition, but it's not clear that those naturally arise from some smooth gravitational path integral. And if so, then it's also possible that maybe replica symmetry breaking might play an effect, so we're not sure about what happens for n greater than 1.
This is just if you have some weird correlation.
Yeah, I just write down some probability distribution over A1 and A2 which is appropriately correlated, so that when I decrease one area, the other one also decreases or something like that. So you can definitely write down.
You can make states like that, and I don't think you'd have replica symmetry breaking issues in its all leading order. But it's just...
Well, the problem is we ignored those off-diagonal terms, which are replica symmetry breaking, right? So at integer n, if there's a saddle,
take a superposition of, let's see, two like macroscopically different geometries. One where the nearer RT surface is nearer extremal surface is the RT surface. And then one where both of the RT surfaces are smaller, but the tiny weighting of one where both of them are much smaller, but the further away one is the RT surface. And that's basically the setup you're talking about. As you go to a radiant entropy, then at some point the one with the smaller entropies will dominate over the larger entropies, larger areas, and it will create a transition because something that...
Sorry, but you mean for n more than 1?
Yeah, for n more than 1.
No, but
so P A1 A2 is peaked at like A1 equals 1 million, A2 equals 1.1 million.
Okay.
Like A1 is smaller than A2, but then there's also some tiny probability that A1 is 1,000 and A2 is 900. So there's some tiny probability down there. Right, so the saddle point is the big one, so the RT surface is A1. But as you go to n strictly greater than 1, then at some point it's going to transition and the RT surface will be A2.
but that's also what Lukowitz Madison did, right?
No, I don't think so. It depends how you think about it.
Let's think about this updated Lewis Malthus version, like whatever. Like, let me just write like this formula. This formula. This would also tell you that. Because I'm scanning over the whole thing and.
Yeah, possibly you're right.
The only issue is like when the saddle fails to satisfy the constraint.
Yeah. Yeah, okay.
Okay, good. So now, let me give you an example, a simple example where this fails. So let's just consider a Gaussian distribution of an area. So I just have some distribution which is peaked at some value where A1 is less than A2. And it's just equal standard deviation in either direction. So it's just the level sets of this distribution are just circles around this point. So at n equals 1, we start at the peak of the spectrum. And then as for n greater than 1, the effect is to just reduce the area. So this red surface is the locus of maximas, the saddles for the cosmic grain arms for the Renyi entropy, and they just move in this direction, and they always satisfy the constraint because we started at a point where A1 was less than A2 and A1 just keeps decreasing further. So there's no problem for n more than 1. But when we have n less than 1, we start moving in a direction where A1 starts increasing, but at some point we hit the line A1 equals A2. And what ends up happening then is it's similar to what Jeff said, which is that the constraint saddle moves along the A1 equals A2 line. So it sort of strictly sits at the phase transition. The dominant effect comes from this diagonal line, which is where this D came from. So if you plot the Renyi entropy, there's the phase 1, where in general what will happen as you move the location of the peak of the spectrum is that there's a phase where A1 will dominate, there's a phase where A2 will dominate, but there's a middle phase where this diagonal piece dominates. And same for the defined Renyi entropy. And this is like this Gaussian distribution is like a reasonable approximation to the peak of the spectrum. So near n equals 1, this is basically what happens for almost any system if you're sufficiently close to the phase transition. But this also happens more generally. So even in these examples with where we had for PSSY, it's the same mechanism. The mechanism is that so even for PSSY, and there's also another calculation on high energy eigenstates. Each of these has the same feature, and the feature is the same. That as you go to n less than 1, at some point you hit the constraint, and then you just stay on this diagonal. So this sort of provides a universal explanation of all of these large order 1 over G corrections to the Renyi entropy. And there's another application to this, which is how we actually landed on this in the first place, which is the entanglement negativity is another information theory quantity which can be computed using a replica trick. And in effect, what ends up happening is that it's actually the n equals half Renyi entropy of a doubled state. So the doubled state is just, it's similar to the canonical purification where you take some system AB, which is just this outer circle, and just double it across the RT surface to get this sort of geometry where you have a boundary of AB and a boundary of A star, B star, which are its doubled copies. And here, the entanglement negativity is given by the half Renyi entropy for the region A, B star. Now, A, B star has an RT surface which is the union of these green surfaces, but it's right at the phase transition. So there's equivalently another RT surface which is the union of the RT surface for A star and B. So it sits exactly in the ballpark where these corrections become important. And so for the entanglement negativity, the correct rule ends up being just applying this modified cosmic grain proposal to compute the negativity. So it's important at leading order for this.
Is this correct? The calculation people previously done With entanglement negativity?
Yeah, so there's a long history to that. So initially people calculated assuming replica symmetry.
Yeah,
so they
yeah.
got this cross-section answer.
Yeah.
Then in fixed area states, there was this random tensor network paper by Ji Dong, Xiao Liang and Michael Walter,
Yeah.
which showed that replica symmetry breaking is important, but
Yeah.
it still left open the question of what happens for general
Yeah.
holographic states, and this answers that. So the replica symmetry breaking does happen, but also you have to be careful about this modified cosmic brain proposal. So what ends up happening is it's a replica symmetry breaking solution where the branes are sort of distributed across the two RT surfaces.
If you're thinking of it as a Renyi half entropy
Yeah.
for the double state,
Yeah.
and is that, I thought the replica symmetry breaking was
Yeah, so replica symmetry in terms of AB itself. So
Yeah.
it's so normally what we do is when you do the replica trick, you take 2n copies, and it's not C2n symmetric, but it's Cn symmetric.
Yeah.
That's it.
Can you comment more on, I guess what Jeff said earlier, so as we go to smaller n, I guess, you
Yeah.
have to make tangent more negative,
Yeah,
and that changes the area until it would force you across a transition.
yeah.
And at that point, you start also adding some negative tangent breaks to the other area.
Yeah, so one way to think about it is so here we plotted
Yeah, that's
everything
right.
as a function of the areas. We could instead think about it as a function of the opening angles at the defects.
Yeah.
So what this is doing is, as we're moving in this direction, it's just increasing the deficit angle at A1, so in this horizontal direction. And that, so it's 2 pi over n. So the opening angle is increasing in this direction, but then you hit a point where the areas become the same. And now, in order to satisfy this constraint, you increase both of the opening angles. So both of them are then increasing beyond that, such that the area stays the same.
But in order to do that, do I have to add 2 different tangent breaks?
Yes, that's right. So the Lucas Martesina problem was there was a fixed tension, and you add it at any one surface. The updated version is you have a total tension which you can distribute on these two surfaces.
But is there something that depends on just n and not on the geometry and particular setting with these two surfaces? So is the tangent, is this total tension just set by n?
Yeah, the total tension is set by n,
And then you get to invent branes
which split it.
which split it.
Yeah, so like fractional branes or something.
I mean, is a path equal that where you allow sort of negative mass states for the matter is always seems a little problematic.
Yeah, that's right. But
And this takes it to another level, right?
yeah, but this it's somehow, I've also always been puzzled about this, like because there's a negative tension brane for n less than 1, but it seems to give reasonable answers. Like
It's an angle on the extreme surface or something. So therefore,
yeah,
the
it is
fractation
an
mode-
extrema. It's not.
So,
Yeah.
so fractation mode can be kind of protected out somehow, right? In a multiple case, that's how negative can.
I'm just wondering how you would define the path equal sort of as a matter of principle in such a way that these rules all arise naturally. I mean, it feels to me like it's just a set of
Yeah.
rules, right? I'm going to pull
Yeah.
out the negative tension. Okay, before we pulled out one negative tension break from the out of what I had.
Yeah.
Now there's an additional rule. I get to distribute this negative tension across.
Well, maybe instead of the tension, like I feel like what this is saying is that the description in terms of the integral over areas was more natural, right? Because there's no funny rule there. Like when we try to translate that to the branes, then it's strange. But in terms of the areas, all it's saying is integrate over all possible values of the area and just the minimal surface has to have this tension.
Well, yeah, I guess when you phrase it that way, you're really allowing, maybe you're saying you're really allowing any tangent, because to do the integral.
Yeah, that's right. But the optimum will have this total tension which is fixed by n and
I mean, okay, yeah, so then from that point of view, I guess it was always Yeah, from that point of view, it's no worse than the original.
It's no worse than the original.
MSS
Yeah,
one.
yeah, it's just different, but
And we somehow should just get on with it with our lives and not worry about the fact that the vacuum is there to produce these objects.
yeah.
Yeah, I mean, I'm satisfied that it's no worse than World War. All right.
Can you go back a few slides?
Oh,
sorry.
Oh,
I just want to look at the proposals.
Oh, yeah, so this is, okay, sorry. This is the cosmic brain proposal?
Yeah, the cosmic brain
Oh, wait.
proposal.
Oh, yeah. Yeah.
Yeah, so with n greater than 1, it's just 2 maximizations, right? So
Yes.
why can I not always exchange those? My level of mathematical rigor, I still always give.
Why can't I exchange those?
So if you exchange the ordering, yeah,
can
and then
exchange
the
those.
first term doesn't depend on I, and so I can bring it to the second term, and then there's a 1 minus n that's negative, and so it becomes a min over AI, and it seems I just get exactly the other proposal for n greater than 1.
I'm not sure that works.
Yeah, it's consistent and you can exchange. It's a minimization.
I think you can exchange, that should be fine.
Yeah, it's
If you
consistent.
can exchange them though, then it's definitely equivalent to your new proposal, isn't it?
Yeah, for it bigger than 1, yeah.
Yeah. N is bigger than 1.
Yeah, that's why.
The only thing that depends on I is AI.
No, wait, sorry. But
You want them to match for n greater than 1, right? You want them to be different, right?
He claimed that with weird setups,
Yeah.
you can have them not match even for n greater than 1.
let's see.
It's not super.
So you're saying, yeah, okay, let me swap these. Wait, what does that even mean?
So,
I mean, so here I'm maximizing over.
so you're just maximizing over A1, A2, and I.
Yeah.
Right, you're maximizing over 3 things. There's a reason you wrote max A1, A2 rather than
Yeah.
max A1, max A2, or the other way around. It's
Yeah.
something that's changed them. And then we bring the max over I inside. It only depends on the second term. The 1 minus n is negative and doesn't depend on I, so you bring it inside that, it becomes a min, and you get your other proposal.
Then I'm not sure you can exchange them.
Yeah, but even if you exchange it, that's like, if you exchange it's exactly the same as you expect.
No, but that's what he's saying. I think that he's saying
At
that
least
they
he
have to
made
agree
it
for n more than 1.
At least if you make them like suprema rather than maxima, then I think you're pretty good. And I think you're assuming, like with a discrete set, then you'd be fine. With the real numbers, you have to worry about like where these things are bounded and so on. But I definitely think you could exchange the maximum to the maximum.
Well, I'll have to think about what happens in the examples where we thought it was.
Anyway, I didn't want to. I think I should let you keep going.
But okay, let's talk about that. But anyway, I was almost done. So so I just wanted to summarize by saying, yeah. So what I did was propose this modified cosmic brain proposal for the holographic Renyi entropy, which was a constrained optimization problem over these area distributions. I showed you sufficient conditions for agreement with the cosmic brain proposal, and I found examples where they disagree, these two proposals disagree. And this modified cosmic brain proposal actually reproduces results in the literature, giving a universal explanation for why the cosmic brain proposal failed. So with that, I'd like to thank you.
Questions for Pratik?
Sorry, just to make sure one point, I think it's why, because we're just discussing, but so there are two maximum, and so the constraint condition comes in when you are doing the first maximum, that
You mean in the modified proposal?
yeah, in the modified proposal,
So here there's a minimization first. I mean, I guess if you wanted to use for n more than 1, you can pull out this and make it a max over 1 minus n times that. And then there's a maximization outside.
Oh, and again go to the previous one.
Yeah.
And you are saying that if we adding the condition that AI is less than A3 minus I, if we adding that constraint, then there's two perspectives.
Even then, it's not all. I mean, I don't think they can be the same because.
Is there something?
What I said was that if the saddles of this satisfy that constraint, then they agree.
Saddle.
But the problems aren't equivalent.
I think if you make that maximization be over things where AI is smaller than A3 minus I. You restricted
Yeah, but
that
that's the same. Yeah, that's the same. I think.
That's what you frame.
That's
why I said only one function f.
Yeah.
In one in w.
Yeah.
But the previous one is only f1.
Yeah.
Find it. f2. Right. And find it. Right. Choose one of them.
Right.
And sometimes you go outside the
Correct.
I just had a comment
Yeah.
that possibly you guys thought about might be helpful. Just in terms of justifying the diagonal approximation,
Yeah.
then I think the off-diagonal terms, you'll have a phase that looks like e to the I mu A1 minus A2, basically just from the introducing the cosmos brains. And that's going to be oscillating very, very fast. I think it's going to be changing at a sort of order 1 over g higher rate than the sort of the magnitude of things changing. And so that would just kill off all the off-diagonal terms.
But there can be real contributions as well, right?
Yeah, there will be real. I'm just saying, like
in this fixed area, you mean this term, right?
yeah, I think you're gonna get.
But in the saddles, mu actually becomes like I times mu or something. Like it takes on, this becomes a real coefficient.
Yeah, it's a good point.
In all
I
of
wanted to
this.
say you take d by d a1 of that thing,
Yeah.
right? Oh, sorry. Yeah, take d by d a1 of that thing,
Yeah.
and you should just get a I mu1.
Yeah.
But yeah, maybe mu1.
Yeah, I think to get these saddles, you have to go into this complex direction
Yeah,
from
yeah,
mu. So
I think that's right.
the saddles end up being imaginary mu. Yeah. Yeah, in fact, we can write down like some of these replica symmetry breaking contributions. It's not obvious that they're always applicable. Yeah.
I had a basic question
Yeah.
about thinking of the views as the large multipliers. So the idea is you want the contribution from having different areas to, so your mu's have to be negative, so that you get a penalty for moving away. Your mu's have to be sort of imaginary.
This mu is, so let's say we integrate over real mu,
Yeah.
then this is just e to the I mu times this thing, which is just a delta function.
Oh.
But then to find the saddles, we can deform the contour to like imaginary values of mu, and that gives you these real defects.
So I thought what you were doing is make like what you wanted to do was to have like an exponential penalty for deviating it away. But that's not
No, that wouldn't help because then the opposite
Yeah.
sign will make it worse.
Yeah.
Yeah. Okay. Questions for Pratik? If not, thank you again.